In our last lecture, we were talking about the introduction to the LPC, the linear predictive coding, and we had shown that how one can relate the linear predictive coding parameters with the speech model that we had studied earlier. Okay, and we had seen that basically the LPC parameters or the linear predictive coding parameters, they follow from the speech model essentially. So, I mean, towards the end of the class we had developed a relationship which goes like this. It was that summation k is equal to 1 to p alpha k, and then we had summation x of n minus j into x of n minus k, which was equal to the summation n x of n minus j, where x of n happens to be the samples. And then we also had that this index j was varying from 1 to p. And what is p? P is the order of prediction, means up to how many past samples are we taking for prediction, and alpha k's were the coefficients which we want to determine, right. So, essentially in this we have got a set of p equations and we have also got p unknowns. What are the unknowns? The unknown quantities are alpha 1 to alpha p. So, what we are going to discuss in this lecture is the computational aspects of these LPC parameters. So, today's lecture will be on the computational aspects of LPC parameters. By LPC parameters we mean these alpha k's, what we need to solve, right. Now, basically there are two very popular approaches or two major approaches to the computational aspect of LPC parameters, because as you understand that basically the problem is posed like this, that there are p equations and there are p unknowns. Okay. So, if we have to go in for the normal matrix inversion methodology, okay, it may be computationally really a great troublesome for us, because I mean all that one has to do is to compute these parameters. I mean this matrix inversion and all these techniques we have to perform within one frame time, because we are fixing up this alpha k's only for one frame time, which can be between 10 milliseconds to 25 milliseconds. Let us say as a figure of merit, let us say I mean as a just a crude figure, let us say that 20 milliseconds of time. So, 20 milliseconds of time computation of all these is not very easy. So, that is why we have to go in for some I mean specialized approaches to the computation of these LPC parameters, and this is what we are going to discuss. Now, for us in the equation that we described in the last class, xn were the samples. So, we took the sample to be the xn's. Now, today before we begin our analysis, we just make some change of notation which I would like to tell you right now. See, what we are considering essentially is that we will consider the segments of speech. So, segment of speech we will be denoting by s, and we will say s suffix n, where suffix n basically refers to that the segment is considered from the point n, right. So, n is the starting of the segment, and from the starting the index or rather the offset beyond that will be denoted by m. So, s n m when we write, this will basically represent the segment of the speech. Okay. So, we are going to have some change of notation. So, that means to say that instead of writing it as n, okay, we should write it as m, because the n notation we are reserving for defining that where the segment starts. Okay. and the index of summation, instead of n we will write it as m, okay. And then with that, okay, with that difference, I mean, instead of writing in terms of x, if we write it in terms of s, the same thing. And then instead of j's as an index, we just use I. So we use I in place of j, I in place of j, and if we do that, then the same equation what we derived last time, okay, could be rewritten as the summation k is equal to 1 to p alpha k, okay. This k we are keeping as the index for the LPC parameters, and this summation, as I have just told you, that should be over m, and then instead of x we are writing Sn, and instead of n we are writing as m, so it is m, and instead of j we are writing I, so Sn m minus I, okay. And then the next product will be Sn, and what it will be? It will be m minus k, and this will be equal to the summation over m. Now here we have to write Sn m multiplied by Sn m minus I, right, and we have to, and we still have p equations. So I index is between 1 to p. So because there are because the I ranges within 1 to p, we have got essentially p equations. So now the focus will be on the solution of these p equations, so that we can determine the alpha case, okay. Now we just define a quantity, okay, which is nothing but the autocorrelation function, okay. Now you just note one thing, that we are writing summation over m, so which means to say that explicitly we are not specifying the limits of the summation, right. So we have kept the limit open ended, okay. So we will specifically put the limits when we go into the specific approach of computation, right. So right now let us leave with an open ended limits of m in the summation, and we define that the quantity summation over m Sn m minus I multiplied by Sn m minus k. This is what we have on the left hand side of this equation, right. So on the left hand side we have this Sn m minus I into Sn m minus k. So this summation quantity of Sn m minus I n minus k m minus k, this we are calling as phi suffix n, and then we have to write this as I comma k. And what is this? This is equal to nothing but the autocorrelation function, okay. So here I, you can say that I is a sort of an initial offset, okay, from the starting, okay, and then what is k? K will be the lag. So essentially the lag in this case is going to be I minus k. In fact, we are going to show that, I mean, just a change of variable, but let us introduce this notation that phi n I k, the autocorrelation we define this way, and in that case, in terms of this equation, I mean this equation whatever we had written, we can just rewrite with the autocorrelation function notation. So we can define it. So we the same equation we just rewrite as summation k is equal to 1 to p alpha k phi n I k. So this is phi n I k, I mean what we have on the left hand side of the equation is phi n I k by our definition itself, and on the right hand side what we have summation over m Sn m minus I. So m minus I remains the same. So this is one and the same as saying that it is summation over m Sn m minus I into Sn m. So Sn m, when we say, then k is equal to 0. So if we put I and then we put for, I mean in place of k we just put k is equal to 0, or rather we can write it as I 0. So, this we can equate to phi suffix n I comma 0. Okay. So, this so here I will be from 1 to p, again p equation. So, it is the same equation we have just written in terms of, rather than writing as summation of Sn m minus I, Sn m minus k of that form, we are writing it in the autocorrelation form. Now, okay, let us keep this equation, and then what we are doing in order to determine these parameters alpha k's are that we are taking the mean square error, and then we are differentiating that with respect to alpha i's, okay, and then we are equating that to 0 and then determining this alphas. So, that is how we approach. So, it is from the minimization of the error consideration, right. So, the minimum mean square error, I mean, if we put this condition and we substitute this into the error expression, then the minimum mean square prediction error. So, the minimum mean square prediction error this will be given by E n, which is equal to the summation over m S n square m, okay. This minus summation k is equal to 1 to p alpha k summation over m S n m S n m minus k, okay, which is equal to, so this Sn square m, how we can write in terms of phi? This is phi n 0 0, correct. So, this is phi n 0 0, and this we already know that this is nothing but the summation k is equal to 1 to p alpha k phi n I k, phi n not I k, in this case 0 k, correct, phi n 0 k. So, this is the expression for the minimum mean square prediction error. Anyway, so now, I mean, let us remember this, and we now go over to one of the computational approaches to the solution of this alpha case, and this approach we will be describing as the autocorrelation approach. In fact, there are two approaches, two very popular approach. One is called as the autocorrelation based, and the other is what is called as the covariance based. So, we will first talk about the autocorrelation based. In fact, the two are related, but you will see that you will first understand that what is the difference in these two approaches. So, first let us understand the autocorrelation method. So, in the autocorrelation method, what we do is that we first of all, I mean, we are taking a segment. Now, are we taking an infinite segment? Certainly we cannot. Although the I mean, in this definition we have put forward, mind you, you must have noted that we have said phi n, we did not say r of n, because we had earlier introduced that we will be calling the short time autocorrelation as r of n, and phi n will be the long time autocorrelation, but we have written the long time autocorrelation expression, okay. But actually speaking, whenever we are computing, it is a finite segment, that is what we have to take, which means to say that we will be multiplying the segment that we are taking by some windowing function. So, we define our S and M, this sequence itself we define as the original sequence S of M, we say S of M plus N into W of M, where M lies between 0 to N minus 1. So, Wm, as you already know, is our windowing function, okay. And if we take a short time segment like this, then we can define the error E of n to be the summation m is equal to 0 to n plus p minus 1 into E n square m. Now, okay, please be careful about this limit. Mind you, so that means to say that the windowing that we have performed is over n samples, 0 to capital N minus 1. But just note that just now the En expression what we have written takes its limit from m is equal to 0 to n plus p minus 1. Okay. So, there is an n plus p term which have come about, and why is this n plus p coming in? Because again, I mean, whenever we are taking the autocorrelation, in that case, as you know that because I mean it will be from p samples, okay, we are predicting. So, if we give a lag of p, okay, we need to have this n plus p minus 1, those many things we require. Now, one point that that you should note at this stage, that always the prediction what we are making will be will not be a good prediction, at least in the initial part and in the end part. Why? Because you see that at the beginning of the segment, when a segment starts, right, how are you predicting the initial samples? From the past p samples? Now, past p samples are what? Past p samples are zeros, because I mean the window has started. So, which means to say that whatever past samples we require, the past samples are zeros. So, the present sample, okay, within the windowed part is being predicted from zeros. So, it is not a good prediction. So, our initial prediction will not be very correct. Again, at the end what we are doing, beyond our windowed part, okay, what we are doing, we are having the sample values as zeros, okay, but we are predicting from the windowed samples which are non-zeros. So, from non-zero samples we are predicting the zeros. So, the solution for that is that we use a window which is not an abrupt window like a rectangular window, but some kind of a smoothing effect, okay, at the two boundaries. And how we can have it? By having hand windows, Hamming windows, something like that, where there is a tapering, at both the ends, right. Now, okay, with this definition of the error, that is what we are doing, that the error is defined from m is equal to 0 to n plus p minus 1, okay. Again we just go over to our definition of phi n I k. So, what is our phi n I k? I mean so what we are doing is that we are assuming that S n m is identically 0 outside the interval m lying between 0 to n minus 1. So, we just assume that S n m is identically 0 outside the interval, we just placed here outside the interval m lying between 0 and capital N minus 1, okay. And then we can show that our phi n I k, our original definition of the autocorrelation, and what we were writing last time, I mean just now whenever I was writing phi n I k, look that I have kept the limit of the summation open ended. I have kept the summation m, but then wrote here S n m minus I, S n m minus k. Now, this S n m itself is restricted, okay, that it is 0 outside the range of m lying between 0 and capital N minus 1. So then whatever infinite summation, if I had intended to write an infinite summation, okay, then the infinite summation now effectively gets truncated to a finite summation, and that finite summation will be nothing but m is equal to 0 to n plus p minus 1, n plus p minus 1, and then we have to write the same thing, that is Sn m minus I Sn m minus k, okay. And in this expression we have to say that how many such ik's are possible. Now I we can vary between 1 and p, okay, and k is for the prediction. So k can also assume a value of 0. So k lies between 0 and p, right. So this is the equation, and now this phi n ik's expression, what we come from the definition, this can now be rewritten in little bit of different form, in the sense that we have what? We have Sn m minus I, Sn n minus m minus k. So let us write it in a write it with a change of variable, so that we want to write with Sn m multiplied by something. So what we have to do, we now have to make just the substitution like this. So by substitution we can express the phi n ik, that becomes equal to the summation of m is equal to 0 to n minus 1 minus I minus k, okay, Sn m into Sn m plus I minus k, okay, and then in this case this phi n ik is nothing but the short time autocorrelation function, okay. So phi n ik now becomes a short time autocorrelation function which is evaluated at the point I minus with a lag of I minus k. So I can write down that phi n ik, instead of phi n ik I can write it as Rn I minus k, okay, where what is Rn k? Rn k is nothing but the summation m is equal to 0 to n minus 1 minus k Sn m into Sn m plus k. So with this definition, just instead of in place of k we put I minus k, and then this equation results. So this equation is effectively Rn I minus k. So phi n ik becomes Rn I minus k. Now again you just note one point, that this Rn k, you already know that Rn k is going to be an even function, okay, the autocorrelation function. So we can write down that phi n ik, now we can write down in this form Rn, and we can say mod I minus k, okay. So I is equal to 1 2 up to p, and k is equal to 0 1 up to p. So this is a good equation that we have obtained, and having obtained that, we can now try to substitute this into our original equation, means what we have to solve exactly, okay. So now right, let us go over to this equation, okay, means we now we are required to solve this alpha k phi n, this equation we have to solve, right. So now in this equation you just put, in place of phi n ik, you just put Rn I minus k under mod, okay, and what is going to be phi n I0? Phi n I0 is nothing but Rn Rni. So I can rewrite the equation, okay, this particular equation I can rewrite as the summation k is equal to 1 to p alpha k into Rn mod I minus k, okay, is equal to Rn I, okay. And how many such equations are there? Same, p equations. So till now, I mean, just note that till now we haven't solved the equation. We are back again to the same equation. I mean, whatever was our starting point, okay, we are back again to the same equation, but okay, just writing in a different form, that's all. So this is 1 less than or equal to I less than or equal to p, and mind you, this equation is no different from our starting point equation of this. So we still need to solve our alpha k's, okay. Only thing is that this summations, okay, we have written in terms of the autocorrelation, short time autocorrelation functions now, okay. So in this form. Now to solve this equation, let us break it up. So after all, what we are going to do, let us take a particular I, let us say that we take I is equal to 1, okay, and now we write down for the summation term. So what will be there? So if we are going to write down for Rn1, we have to just substitute I is equal to 1 over here. So what are we going to write on the left hand side? Alpha 1 Rn, it will be mod of 1 minus 1, because I is 1. So this equation we are writing for I is equal to 1. So that means to say Rn of 0. What will be the second term of the solution, second term of the left hand side? Alpha 2 times Rn, and what is mod of I minus k now? Now k has become 2, and what is I? I is still 1. I is, I mean, this equation we are writing for I is equal to 1. So I is 1, k is 2, so Rn mod of minus 1. So this means to say it is Rn 1, right. Third term, alpha 3 Rn 2, okay, and plus so on. And if you want me to write down the last term is going to be for k is equal to p, and I is still 1. So it is 1 minus mod of 1 minus p, which is nothing but p minus 1. So I can say that alpha 3 Rn p minus 1. So this whole thing, this summation series is going to be equated to Rn 1, right. Now we make I is equal to 2. So we compute Rn 2, right. So Rn 2 will be equal to what? Again alpha 1 we have to start with. This time what are we going to write? Alpha 1 Rn, this time we have to write 1 because I is 2 and k starts with 1. So 2 minus 1, 1. So alpha 1 Rn 1. What will be the second term? Alpha 2 Rn 0. What will be the third term? Alpha 3 Rn 1, okay, plus so on. What is going to be the last term? No, this is not alpha p, last term coefficient is alpha p. So this is alpha p Rn p minus 2, right. Symmetry is definite, but you will see another interesting property of symmetry. Okay, so this is, I mean, as some of you must have already noted that this is resulting in a matrix equation. So I just write down I is equal to 3, which you can now understand very easily. It is going to be alpha 1 Rn 2 plus alpha 2 Rn 1 plus alpha 3 Rn 0, okay, plus so on, and it will be alpha p Rn. This time it is going to be p minus 3, which is going to be Rn 3, and so on we go on, and the last one will be alpha 1 Rn p minus 1 plus alpha 2 Rn p minus 2 plus alpha 3 Rn p minus 3 plus so on, and the last term will be alpha p Rn 0, which will be equal to Rn p, because the last expression we have to substitute I is equal to p, right. So now we have got p equation. So we have explicitly written down the p equation. So as people have already noticed that it is going to be a matrix form of representation. So now let us represent this set of p equations into matrix, and what results is something like this, that we can write down a matrix, and this matrix will have elements Rn0, Rn1, Rn2 up to Rn p minus 1. Next row will be Rn1, Rn0, Rn1 up to Rn p minus 2, Rn2, Rn1, Rn0, last term Rn p minus 3. Last row is going to be Rn p minus 1, Rn p minus 2, Rn p minus 3, and so on up to Rn 0, and this will be this matrix. This is a matrix of what size? P by P. So this is a P by P matrix, okay, and the P by P matrix will be multiplied by a column vector. So that column vector will have elements what we want. So we want to solve for this alpha 1, alpha 2, alpha 3 up to alpha p's, and this is available here in the form of a column vector, and this will be equal to what? Another column vector. And what is this column vector? What we have written down on the right hand side. Okay, so Rn1, Rn2, Rn3 up to Rnp. So this will be Rn1, Rn2, Rn3 up to Rnp, right. So this is nothing but same thing. I mean, whatever we had written in summation form, we have written in a matrix form now. And one of the participants here have already pointed out that it results in a symmetric matrix. Indeed so, because you just see Rn1, Rn1. There is symmetric about the diagonal. Rn2 here, Rn2 here, Rn1 here, Rn1 here. And other than the symmetry, you notice yet another interesting property of this matrix. Just travel along the diagonal. What are you seeing? All the diagonal elements are the same. Travel along any diagonal, take Rn1, 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 and here it ends with Rn1. Instead of doing that, you take Rn2, you travel along Rn2, you will always find Rn2. You find along Rn1, you will always travel along Rn1, you will end up in Rn1. So the diagonal elements are the same. So it is not only symmetric, but the diagonal elements are the same. Can anybody tell here that what is this matrix known as? Anybody dealt with this matrix? Yes, the correct answer has already come. This is called as the Toeplitz matrix. Toeplitz matrix. right, very interesting matrix. So it is not just symmetric, but it has got a Toeplitz matrix, the beauty is that very nice solution techniques, iterative solution techniques are available already for Toeplitz matrix, and we can make use of that in order to solve for this alpha 1 to alpha p's, because after all what we are supposed to do here after this, okay, I mean you just write down in a matrix, you pre-multiply both this I mean this whole matrix equation by the inverse of this matrix. So what do you get? You get alpha 1 to alpha p as a vector on the left hand side, and on the right hand side you get inverse of this matrix times this. Okay. Now correlation, the autocorrelation values you can compute, you just look at the speech samples, you compute the autocorrelation values, that is not a problem. So everything here is known, all the elements are also known, elements of this matrix, but only thing is that we want a good technique for carrying out the inversion, and because of this Toeplitz matrix property this will really help us. Okay. Now the solution of this equation using the Toeplitz matrix solution approach, that we will show shortly, okay, may not be in this class, but in this class what I want to do further is that we will now explore the second technique of solution. One approach is this approach is called as the autocorrelation method, and now I will introduce you to the second approach, and which we will be describing as the covariance method. So we will now treat the covariance method, and then I promise to come back again to solve for this Toeplitz matrix part, okay, in order to make it based on the autocorrelation approach. So now I will deal with the covariance method. Now the covariance method of solution, essentially it does almost the same thing, okay, but you will be seeing that the definition of the error is little different. So that is why the index of the summation looks different. Did you notice one thing, that when we were talking about the autocorrelation approach, where did we talk of? We talked of that during our pitch detection. Okay. Now there we had said that whenever you are taking the short time segment, the problem happens that whenever you are giving some lags to it, okay, the overlap period, okay, is becoming less. So that is why ideally we wanted that if we could have an autocorrelation with an extended sequence multiplied by the original windowed sequence, okay, or rather convert with the original sequence, in that case essentially it is not the autocorrelation anymore, but as if to say it is the covariance with the extended sequence. So we that time called that approach as the modified autocorrelation based approach for the pitch detection. Now we are going to do something very similar over here. So what we are going to do is that we will now define our En, that is to say the error, to be the summation m is equal to 0 to n minus 1 of E square n m. Now this is very interesting. So that means to say that we want that for all these n samples the error signals must be computable, right. So this is different from our error definition that we had used last time. Just have a look at what definition we had given earlier, right. For the autocorrelation method we had given the definition as En equal to En square m, but m is equal to 0 to n plus p minus 1, whereas in this case we are giving m is equal to 0 to n minus 1, right. So just note that the limit is different, but the limit difference, okay, makes a lot of difference in this expression, although deceptively it will appear that as if to say that we are redoing the same thing. Now, if we have this, then our phi n of I k, okay, phi n of I k now becomes the summation m is equal to 0 to n minus 1 S n m minus 1 into S n m minus k, okay, and this what we have to do for I is equal to 1 to I lying between 1 to p, k lying between 0 and p. And if we change the index of summation, okay, in that case we can write down phi n I k to be equal to the summation m is equal to minus I to n minus I minus 1 S n m into S n m plus I minus k, okay, I 1 to p, k 0 to p, okay, or we can also write down as phi n I k, which was equal to summation m is equal to minus k to n minus k minus p into Sn m plus k minus I, again I between 1 to p, k between 0 to p, right. Now, again you just see that last time we had a similar definition, but what did we say? M is equal to 0 to n minus I minus 1, and why did we do that? Because we had assumed that Sn m is 0 outside the interval. We had said that Sn m is 0 outside the interval m varying from 0 to n minus 1. Now, if we have to compute our phi n I k by this expression, okay, where we want the limits of summation to go from 0 to n minus 1, then in order to solve, in order to have this phi n of I k, we must have an, I mean this is equivalently an approach like this, that is what we have to follow, and in that case we cannot want, we cannot have the Sn m values to be zeros outside this interval, okay. Either before that, I mean either before 0 you make the samples up to index minus I or minus k, you make them as zeros, okay, or otherwise you just extend it, I mean up to n minus 1, so that you really get the product or the correlation, okay, up to that stage. So, this basically calls for the extension of the sequence, because now we need values of Sn m in the interval p to n minus 1. So, we need Sn m in the interval m between p and n minus 1, okay. Now, if so by having this limits of En, okay, now we can write down the equation, that is to say our original equation, okay, involving the alpha k's and the summation of product terms, okay, which we are calling as the autocorrelation term. So, alpha k's times the autocorrelation term equated to another autocorrelation expression, the same thing remains, but now in this case we are going to write it as the summation, the set of equations now become k is equal to 1 to p alpha k phi n I k, which is equal to phi n I 0, okay, for I is equal to 1 to p, okay. And now we can I mean have again again it is a set of P equations, okay. But I mean looks very similar, but in this case we will not be able to equate it to the Rn terms, but rather we have to keep it to the phi n terms, and the kind of matrix that results is like this. So, this will be phi n 1 1, phi n 1 2. I mean you just expand this equation, I am not writing or explaining because this is quite obvious. Phi n 1 p, that means to say all the first row elements, okay. Then I write the second row elements, phi n 2 1, phi n 2 2 up to phi n 2 p, and the last one I am writing directly phi n p 1, the pth row, phi n p 2, and it ends with phi n p p. So, this is also a p by p matrix what I wrote, and here as usual it will be alpha 1 up to alpha p, the column vector, and then we have to write here again this phi n. It will start with 1 0 in the first row, it will be phi n 2 0, and last will be phi n p 0, right. So, this is the matrix equation that we have. Now, just can you tell me that can any property result out of this matrix? Is it symmetric? Yes or no? It is symmetric because phi I k, phi n I k is same as that of phi n k I. It does not matter, I mean our by the basic definition itself, it does not matter whether I interchange this order of I and k. Instead of I and k, if I write k and I, okay, it is going to remain the same. So, phi n 1 2 is going to be phi n 2 1, okay. So, it is symmetric about the diagonal. Only thing is that it is not Toeplitz, but it is a symmetric matrix. So, I mean there should be good techniques for its inversion also, okay. I mean may not be like the Toeplitz matrix, but even inversion of this should be possible. And in fact we first show you the solution of this, okay. Maybe in this class, if I do not have the time, I will continue with the approach in the next one. I just basically introduce the solution approach. In fact, this equation what I have written down, okay, I can write it down in the form of a matrix equation. Now, matrix equation, for that I just use a different color pen. Let me use a red color pen to give you the matrix equation. So, this is phi times alpha is equal to psi. So, this is the matrix equation representation of what we have written down over here, okay. Now, only thing to notice that here what I write by phi is a phi matrix, right. Alpha, this red alpha is nothing but the alpha as the column vector. So, I should better write this as alpha vector, and this one, this is another column vector, this phi n 0 0. So, this also is a vector. So, this is a vector, this is a vector, and by the matrix notation I should also write down this as, and this is a matrix, not a vector exactly, but phi alpha is equal to psi. This is the basic matrix equation which we have to solve. Our objective will be now to solve this alpha, but to solve this alpha, okay, we have to make a manageable form of this phi, right. Phi, as I said, that phi is a symmetric matrix, that property is known, and in fact phi, this phi matrix will be represented as I mean in this form, that it will be a V matrix multiplied by the D matrix multiplied by V transpose. Okay, so I was actually dictated by one of the participants, so who must have known this approach very easily. So let me ask that what is that approach? This V, what is D first? D is a diagonal matrix, and what is V? V is triangular matrix. No, D. So V is a triangular matrix. So this is the upper triangular matrix. That's what we have to do. So now what results basically is that this will be referred to as the square root approach, right? I mean, if I express the phi matrix in this form, then that method is called, this decomposition form is known as the Cholesky decomposition. Okay, so this is referred to as Cholesky decomposition solution of the covariance method. Okay, or this is also known as the square root method. This is popularly known as the square root method. Okay, or this I mean, so sorry, V is actually the lower triangular matrix. So V is the lower triangular matrix. Okay, and in fact this is a lower triangular matrix, okay, whose diagonal elements are all ones. Okay, so here the diagonal elements are all ones, right? So we will be making use of this phi is equal to this, okay, in order to solve this basic equation. And in fact before we approach a solution of this, first let us try to express this phi in this manageable form. So if we can somehow solve for the elements of this V matrix and the D matrix, okay, that should help us, because from the using this V matrix and D matrix, the solution of this alpha vector would become much easier. So to solve for the V matrix and D matrix elements, what we will, the approach that we will be taking is that we will equate the ijth element of this phi matrix with the ijth element of this product matrix. Okay, and if we just equate the ijth element, then the ijth element equation would look like phi n ij. Mind you, now there is no more of vector or matrix notation. Now I am back again to the scalar. So phi n ij is equal to summation k is equal to 1 to j v I k into d k, that is to say the diagonal matrix element, into v j k. Okay, and this j lies between 1 to I minus 1. Okay, so this is the ijth element of the phi matrix being equated to the ijth, corresponding part of the product matrix, that is VD V transpose matrix, what we have written down, its equivalent form ijth element is being written here, and that will give us a starting point, okay, to solve for the elements of this V matrix and the elements of the D matrix. Once we solve for the elements of the V matrix and the D matrix, okay, rest of the solution for alpha would become pretty straightforward, right? So this is what we will be showing you in the next class, okay, and also this will be followed by the methodology for autocorrelation method solution, means where we have to do the inversion of the Toeplitz matrix. Okay, so thank you for today.